We're continuing with section 2.1, and I thought I'd take a look at a couple of exercises from that section. So the first one is 2.1 number 31. And then this one, it says solve the IVP below. Do you remember what an IVP is? IVP stands for initial value problem. And so our initial value problem is y prime minus 3/2 y is equal to 3t plus 2e to the t. And we have y of 0 is equal to some constant y sub 0. Okay, so if we want to solve this, this is a linear first order differential equation, and it's already in standard form with our little p of t being 3 minus 3/2. So therefore the integrating factor is just e to the minus 3 over 2 times t. Multiply both sides by that, and I'll just go ahead and skip over that step. Oh, maybe I better not. Okay, multiply both sides by e to the minus 3/2 t. Let's see here. Minus 3/2 times e to the minus 3/2 t times e to the t would just be a minus 1/2 t. Okay, so then, of course, the idea behind the integrating factor is that this whole expression becomes y e to the minus 3/2 t. Okay, and then this b just drops down. All right, so now to solve this, I need to integrate everything. And so if I want to integrate 3t e to the minus 3/2 t, sorry about missing the t there. How do I do that? Why, yes, it is a table. And so here we have or e to the minus 3/2 t. Okay, so this would be what? To get a 1, that's going to be a minus 2/3, and this would be 4/9. Okay, and so then integrating, what do we get? Looks like we get 3t times minus 2/3, which is minus 2t, e to the minus 3/2 t. Minus 3 times 4/9 would be minus 4/3, e to the minus 3/2 t. Good. And then our other integral is 2e to the minus 1/2 t. And so for that one, what do we get? Looks like we get 2 times minus 2, right? E to the minus 1/2 t. Oops, we're not going to put in our plus c yet, but we will in just a second. So that's going to be minus 4 e to the minus 1/2 t. Good. So let's put all this together now. We have y times e to the minus 3/2 t equal to minus 2t e to the minus 3/2 t minus 4/3 e to the minus 3/2 t minus 4 e to the minus 1/2 t plus c. There's our plus c. Good. And now we divide both sides, which means we multiply by e to the positive 3/2 t. And what do we get? Let's see, it looks like we get minus 2t from that term. And then from this term we get a minus 4/3. And then from this term we get, let's see, minus 1/2 plus 3/2. It's just a plus 1, right? So that's going to be minus 4 e to the t. And then we have plus c e to the 3/2 t. Good. And now we have our y of 0. So let's plug that in. We have y of 0 equals y sub 0. So that means y sub 0 should be equal to, let's see, 0 minus 4/3 minus 4 plus c, right? So it looks like c is equal to y0 plus 16/3. Good. So now I think we're ready to write down our answer. Y of t is minus 2t minus 4/3 minus 4e to the t plus y0 plus 16/3 times e to the 3/2 t. Very good. All right. So how is this expression going to work? I think that we have an e to the t there. So let's maybe look at this. This expression might be easier to look at first. This one. So what I'm seeing here is that if the c is positive, then where is this function going to go as time gets very large? If c is positive, then this term is going to dominate the expression, and so this has a negative coefficient in front of it, but this exponential function is going to be able to overtake that, so to speak. On the other hand, what happens if c is equal to 0? If c is equal to 0, this term's not here, and so then what happens to your solution? It goes to minus infinity. So for some solutions, for some values of c, the solution goes to minus infinity, and for some solutions, for some values of c, the solutions go to positive infinity. Is there a way to tell which is which? Well, it's when c is equal to 0. That's the breaking point, right? That's the divergent point, I guess you could say. So therefore, coming back down to our original expression, if y0 is greater than minus 16/3, right? Then c is greater than 0, and y of t goes to positive infinity. And if y0 is less than or equal to minus 16/3, then c is less than or equal to 0, and y will go down to minus infinity. Good. So that solves number 31 in section 2.1. Good. There's another problem. We're not going to go too deep into these. It's just kind of a fun thing to think about. So if this is 2.1, number 37, for example. We'd like to find or construct y prime plus p of t times y equals g of t, so that y converges to a function, let's say 4 minus t squared, as t goes to infinity. Okay, probably the easiest way to think about this is that when we were doing problems before with constant coefficients here, it was easier to construct such a differential equation. So suppose that whoops, I just lost my page. Suppose I say that instead of this general form, let y prime plus a times y be equal to g of t, and let's see if we can get a solution to that. So what is the integrating factor? It's going to be e to the at, right? And so when I solve this differential equation, I'm going to be multiplying both sides by that. Right? And then I'm going to be integrating this side. However that works out. But then on this, I'm going to have a plus c, right? And then I'm going to have this integral plus ce to the minus at. And so as long as our a is negative, or sorry, as long as our a is positive, we're going to be able to solve that. So let me write just arbitrarily, let me just take a to be equal to 1. So let a be equal to 1, and then we have our y prime plus y equals g of t. And now we want our solution to be y equals 4 minus t squared, and then we're going to have plus ce to the minus t hanging out here at the end. Okay, so now what is our g of t? Well, you can plug this function into the differential equation and see what you get. So what do we get for y prime in this case? Minus 2t minus ce to the minus t. And so if I add these two together, notice that the c's drop out, and you're left with y prime plus y is equal to 4 minus 2t minus t squared. And this is your differential equation. So that's what I think what made this problem hard, is that there's a couple of arbitrary choices that you could make here. So for example, the first one was that we could make this a constant, and the second one was that we could actually even define the constant to be equal to 1, and so you could just start off with this equation instead. And then once you get the general form for your solution, then you can figure out what your g of t is. Good, and I'm over time, so I'll stop there.